now we have almost all we need to completely do functional programming in the functional paradigm. We need just three more little concepts, which I'm going to show right now, which is function composition, the ability of a function to call another one, function recursion, the ability of a function to call itself, and the conditional statement, the ability to change execution depending on the value of a calculation. So let me start by showing what function composition is. So let's say I want to define a new function, sum digits 6, which gives the sum of digits of a 6-digit positive number. Well, I can use sum digits for the 3 top digits and the 3 bottom digits. So for example, I call sum digits with n div 1000. This gives me the top 3 digits, and then I add sum digits of n mod 1000, which gives me the bottom 3 digits. So sum digit 6 is defined in terms of sum digits. So this is called function composition. So for example, I can do sum digits 6 of 314159, and this returns 23, which is the sum of the 6 digits. Okay, that's one thing. But let's say I want to go one step farther now. Let's say I want to have one function, sum digits, that calculates the sum of any number of digits, up to the maximum that I can represent, but any number potentially. Well, I can do that also in a single function. So let me call it sum digits r. And with this, I'll use another technique called recursion, dividing up a large problem into smaller problems. So I will do the low digit, n mod 10, and then I will add some digits of the number where I chop off the low digit, which is n div 10. R n div 10. Let me put this in parentheses and write it like this. So this is potentially a good solution, where I will take the smallest digit and then I will use for a smaller number. But this particular definition is not correct. There's something wrong. I keep chopping off a digit, going smaller and smaller and smaller, but I never stop. Once it gets to 0, it keeps going. So I need one more idea now to make recursion work. That is the ability to change what I do in what I execute depending on the result of calculation. So I will do something like this. Let me first take the program existing. Let me now fix it. I will use an instruction called an if, a conditional. If n equals 0, then I stop. Otherwise, I go on. So this is else, and then end. So this is a better definition. It uses the same idea of recursion, but it knows when to stop. So if n is equal to 0, the result is 0. Otherwise, else, I do the recursive call, n mod 10 plus some digits of n div 10. So this function should be correct. So you see the ability to do recursion has to be combined with the ability to do a conditional, to do a different execution depending on the value of the calculation. So 314159, this should give the same result as before, 23, but now we can go farther. We can say, for example, 31415926535589, and this gives 61. So with these three abilities, function composition, function recursion, and conditional, we have now a complete language which lets us do anything that any programming language can do. So let me now summarize to tell you what we've done to turn our partial language into a complete programming language that lets us program in the functional paradigm. So first of all, we have function composition. And here we show the example of sum digit 6, which calls some digits, so a function calling another. This is a key ability for building large systems because it lets you build systems in layers. Each function calls functions in the layer below, and in fact, practical systems can have hundreds or thousands of layers like this. And this is the first step toward data abstraction. But it's not enough. We need more. So the next thing we need more is what's called recursion, a function that calls itself. So here is the sum-digits function that works for any positive integers. So sum-digits r will call itself with a smaller number. Okay? But this particular definition is buggy, it's wrong, because it never stops. We need something to make it stop. So we need another concept. This is the conditional or the if statement. Here, the if condition, this is a function that returns true or false, a Boolean, which is called a Boolean. So if n equals 0 is a function that compares n to 0 and returns true or false. If it's true, it executes the expression after the then. If it's false, it executes the expression after the else. And like all compound instructions, it ends with the end keyword. So recursion with the conditional statements is enough. We now are able to calculate a complex function by going to smaller functions, and now we know how to stop. So this is function recursion. Function recursion is a very important concept. It's a key ability for building complex algorithms, because many complex algorithms, complex systems, consist of smaller systems that are combined together. So we divide a complex problem into simpler subproblems. This is a technique called divide and conquer. So recursion is a very important general technique for that. So now we have arrived at the complete functional paradigm. So what we have arrived at, the ability to calculate with numbers, expressions, to define functions, to do function composition and recursion, and to use a conditional to stop. This is a fully capable programming language. And in fact, we say it is Turing complete, since it computes the same set of functions as a Turing machine. So a Turing machine is a particular, very simple kind of computer defined by Alan Turing in the 1930s. And it's important because it can calculate all the functions that we know how to calculate using computer programs. So our functional language is now this as powerful as a Turing machine. And in the next lessons, we will see how to harness this power. In particular, we will use the power of recursion. We will only use a small subset of recursion in the next two lessons, the looping subset to do invariant programming and symbolic programming. But later on in the course, we will continue to harness the power of functions, recursion, and function composition in techniques called higher order programming, data abstraction, and also in concurrent programming.